So I'm going to be talking about connection between gradient descent, gradient SGD, kind of gradient flow type algorithms, and sampling, especially gradient-based sampling. Yeah, and kind of the connection is going to be through Lyapunov potentials. So most of this is kind of joint work with my student and past student. August is my current student. Ayush was my past student. Okay, so without further ado, I'm going to directly jump into kind of the settings that we're going to look at. So our goal kind of on the optimization side, our goal is to minimize this function f of x. Okay, and if we are in the deterministic optimization setting, we get access to the gradient of f of x. And the most common algorithm out there for this problem is gradient descent. You can also think of kind of the stochastic version of this where f of x can be seen as expected some small f of x, where z's are kind of instances drawn from some fixed distribution. And in this case, what we get are estimates of gradients, or in other words, you get an instance that's drawn from the set, from the distribution D, and you get to see the gradient of the loss under this distribution. And what we know is that it's an unbiased estimate. Okay, so this is a setting that I'm assuming many of you have seen before. Another goal that typically happens in sampling is you want to draw instances from this, or you want to sample from this distribution whose density is P of x, which is given, which is called the Gibbs distribution. Its density is proportional to e to the power of minus beta times f of x. Okay, and typically beta is kind of, it's the inverse temperatures, kind of, sorry, it's a temperature parameter in this setting. Okay, and again here, since you guys already attended Dheeraj's talk, you already know it was written in slightly different form, but essentially the gradient of f here, that's exactly what was the score function there, right? And if you look at the techniques that were used kind of for the sampling, one of the commonly used techniques is Langevin Monte Carlo method, where in some sense what you do is just gradient descent plus noise. And what we wanted to understand is, are there connections between the two, and can we kind of harness this connection? Okay, so to kind of put both of them in the same slide, you have the optimization, which is minimize f of x. We have sampling, which is this. And one of the cases where we really well understand this problem is when capital F is convex. So if f is convex, we know fairly well how to optimize it using gradient descent. We know the kind of rates we get, et cetera, et cetera. And when f is convex, we also know how to sample from it. And in this case, the distribution is what's called log concave distribution. We know how to sample from this. And you can kind of think about the goal of what we're doing now is to go beyond this convexity to go into non-log concave distributions or non-convex f's. And when do these methods work? Okay. All right. So again, to remind you, gradient descent is just this simple algorithm where on every step, you take the previous iteration minus some step size times gradient at the previous step. That gives you the next step. This is the stochastic version. And there is also this gradient Langevin method where you just add a little bit of noise in there. Okay, so these are all kind of typically seen as optimization methods. The advantage of the last one is if there are small kind of areas of local minima, it jumps out of it because of the noise added in. Okay. Okay. On the other hand, you have Langevin Monte Carlo sampling, where again, really what you do is kind of the same thing. You essentially do gradient descent plus add noise. And if you add noise with the right beta parameter, you can show that you will be sampling from the original distribution. Oh, you mean this and this? Oh, sorry, yes. This should be lowercase f. This should have been this guy. Should be the smaller gradient. So the idea is that kind of typically whenever the gradient descent, the deterministic one works, if you sample one at a time, you should also be able to, usually you should also be able to show that you get a learning algorithm in the sense that you only get access to the small f's, but then you are actually optimizing capital F. Right? And while it works here, so wherever I put stochastic, just think of it as small f. That's my error, sorry about that. Okay. So the questions that we are interested in is when do these algorithms work and what's the relationship between sampling and optimization? Okay, and to some extent, is there a unifying framework or technique? Okay, Actually, I'm going to skip the outline. Good. So I'm going to start with kind of the idealized version or the continuous time version. In the continuous time version, you can write down gradient flow by this differential equation here. I am fairly certain at this point, most of you would have seen this in some form or the other. You saw the noisy version of it when Dheeraj presented it, right? And again, x of 0 times 0 is the initial point. And throughout this talk, I'm going to assume that f, okay, I don't really need to assume that f is minimized at 0, but I'm going to assume that f of the minimizer is equal to 0. Okay, so I'm not going to write the difference between the f's. And so basically when I say f of xt, that's the suboptimality of f of x of t. And our goal is basically given an epsilon, we want to kind of ask how much time do we take before we can get a point such that f of x of t is less than or equal to epsilon.
Sorry, I have a question.
Yeah.
I'm just trying to understand the motivation of when you say how, when does it work? So is this would you say it works only if it finds the global minimum? Is that the definition of works?
Yes. So, okay, no, actually, as I mentioned here, the goal is you give me an epsilon. So the idea of when it works is you give me any epsilon. I'm going to give you a time that's a function of epsilon such that f of xt is less than or equal to epsilon. Right? If f of xt is equal to 0, that's achieving the exact global optima. I don't really care about going all the way there because I'm happy with epsilon errors.
Here is to make sure it doesn't get stuck in some local minimum somewhere because you know it'll flow to a local minimum
right.
sometime.
Okay. Right. Again, I don't know if I'm going to be answering the question you have in mind, which is in the sense that, so I'm going to kind of, to some extent in this talk, I'm going to assume that gradient flow works, or I'm going to kind of write down if gradient flow works, what are the conditions that will hold, right? And then kind of talk about what we can do in terms of gradient descent, one, and also the connection to sampling and so on. Okay, but again, it works basically means that if I run this process for enough amount of time that depends on epsilon, I get this condition. That's what I mean by work. Okay, and I'm also going to talk about tau epsilon of x naught, which is the smallest time such that if I run this process, it's going to hit that epsilon suboptimal set. And this is especially going to be useful once we add the noise and stuff, right? Because it could go hit it, come out, and so on. So it's typically called the hitting time. Okay, so again, this slide again needs no introduction. It's the same thing as before. Here, I'm going to have the stochastic differential equation. This is exactly what you saw in Dheeraj's talk. You have the gradient of f of xt. So that's, if I didn't have the second part, that would have been gradient flow. I have this extra Brownian motion added in. Okay, and again, here I'm going to define more formally what the hitting time is. It's the first time that I actually get to this epsilon suboptimal set. And typically, we would expect that we want to kind of look at scenarios where this quantity is well behaved. Okay, and kind of the goal, so the first part of the goal is that we want to ask, okay, if these idealized time versions, that is the continuous time versions, have nice guarantee, then what can we say about kind of running a discrete time version, or how do we kind of think about discretization? Okay, so one more definition that we want to get out of the way is the notion of a generator. So given this process x of t, we are going to call the generator is going to be defined as the following. I'm going to assume that the functions are nice enough such that this exists. So the generator for a function f is, let me take limit t tending to 0 of f of xt minus f of x, where x is the starting point. So think of this as x of 0. Okay, so that's the generator. And what you can immediately figure out through normal calculus is, for the gradient flow process, it's just the gradient of f times whatever f you're applying the operator to. That's the generator for evaluated at point x. And for the diffusion process, this pretty much comes out of Ito calculus. You have the same thing, plus you also have this Laplacian term. And again, you guys have seen the notion of Laplacian in Dheeraj's talk. This is the Laplace operator, and we're going to apply it to whatever f that we're going to kind of look at. Okay. Okay. With all of this, so think about the version where this is just gradient flow, right? This is basically saying it's kind of at an infinitesimal rate. kind of what does the, what does this, like, what's the rate of change of the function, right? So, I mean, for the gradient flow, you can actually write this down. This is d of f of xt divided by dt. Right? That's what this is. Yeah. So in this definition, capital F is always what it is, right? We are doing gradient flow with respect to capital F. And I'm defining this L to be an operator. And here I'm just showing if I took any function small f and applied this operator, this is what it would look like. X of t always varies according to capital T. Maybe I should have used a different notation for the small f, maybe some other alphabet. Is the process, yeah. So yeah, this x here is just kind of, I'm going to start at that x, and then I'm going to ask kind of what does it look like if I infinitesimally move according to whatever the process is, right? And then if it is a stochastic process, I'm taking the expectation here. And essentially, this guy is pretty much kind of take the path. I mean, if you kind of think of this as the path, I mean, this guy is just literally just the definition of derivative, right? And this guy comes out of Ito calculus. Okay. All right. So great. So now with all of this, I'm ready to define kind of the notion of Lyapunov potential that we look at. We're going to say that a function phi is going to be a Lyapunov potential with respect to some open set A if the following happens. So it has to satisfy the fact that phi is greater than or equal to 1, okay, for every point you evaluate it at. And on the set A, we should have that minus the generator is an upper bound on some lambda times phi, okay? This is what we're going to ask for. And typically when, so this is the definition of Lyapunov potential that's commonly used. For our setting, the way we're going to think about our set capital A is we're going to think of it as all the points that are outside of the suboptimal region, right? So where we want to hit is A complement. We're going to think about A as everything that has suboptimality strictly larger than epsilon, okay? So there is no randomness, right? Because the randomness came, I mean, like the Lyapunov, sorry, the generator was, I mean, the generator did not have any randomness in it. You give me the process, the generator just says expected f of, expected, so limit t tending to 0, expected f of x of t minus f of x of 0, let's call it, right, divided by t. This was the Lyapunov potential, right? So whatever, so my initial point is like fixed. Starting from that initial point, whatever randomness is there, I've integrated it out, right? So this operator, so this is what I'm going to define as L of f of x for a particular point x, right? And so this is, there is nothing random about this.
The process x of t is...
X of t is random, yes, but that's, I'm integrating it out here. No, x is not random. This is, I mean, I'm defining this operate. So L of f on a particular x is defined as on any open set. It's sorry, for a Lyapunov potential with respect to a set A, it's a valid Lyapunov potential if phi is greater than or equal to 1 and minus the generator is larger than lambda times phi. Okay, and the claim here is that if you have such a potential and it has nice enough properties, so for instance, if it's smooth, then if you have this with the corresponding generator being for the gradient flow, then you get a gradient descent algorithm. And similarly, if it is with respect to the Langevin dynamics, and if it is smooth enough up to the right order, then you can get that SGLD works. That is or GLD works, gradient descent with Langevin.
Karthik, any conditions on lambda here?
Oh, lambda is, so lambda I'm assuming is greater than 0. It's just some constant.
Okay.
So yeah, lambda is greater than 0. I should have put that. Yeah, lambda cannot be negative, but as long as you have some constant lambda strictly greater than 0, you're fine. Okay. Okay, for now, let's see kind of why this potential would help us. Okay. So I have this on the slide, but I would prefer to do it on the board. So the idea here is that if you ran gradient descent with an appropriate step size, then it guarantees that it's going to go to the epsilon suboptimal region. And the proof is extremely simple. It's literally just apply Taylor's theorem, up to second order, and you would basically get it, right? So the idea is that if I look at P of X of T, this guy, I can write this as equal to do I do TT minus 1? Okay, I do TT minus 1, good. Xt minus 1 minus eta times gradient f of xt minus 1, right? And this guy, I can write it as xt minus 1. Actually, I'm just going to use this guy. See, maybe I don't need to do it on the board. Let me just go over the slide. It's easier. Okay. Where did it go? Okay, so the first few steps are simple enough. Kind of xt is defined as xt minus 1 minus the gradient. Do a Taylor expansion. And as I mentioned, I'm going to assume for now that the potential is smooth, H smooth. So, and I'm going to assume that the function that we are minimizing is Lipschitz. So this is just to give an example. In reality, you don't need smoothness of phi or the Lipschitzness of f. You can deal with more generalized notions, kind of where you can show that the derivatives that you're interested in are upper bounded by the function value itself or some monotonic function of the function value. So H smooth basically means that the largest singular value of the Hessian is upper bounded. Right? And so you essentially that gives you this. So if you write down Taylor expansion, it's the Hessian at some intermediate point, and then I'm just kind of upper bounding it by capital H times identity. So that gives me this equation here. So you get gradient f with a minus sign times this guy. Okay, and now the main idea here is once you arrive at this point, I've used the Lipschitzness here to remove the gradient and put an L squared. The main thing that you notice here after this is that our assumption was that the negative generator is lower bounded by the potential. And now because we have minus of the negative generator, or in other words, so because we have minus of the negative generator, it's upper bounded by minus phi, minus lambda times phi, and that's all the way till here, okay? Once you come here, now pull the eta times lambda all the way to the left and sum over these guys, right? So what do you get? On the right-hand side, your phi of xt minus 1, that gives you a nice telescoping sum. And so you end up with the following, that your average phi is upper bounded by phi at x naught, which is the starting point, divided by eta times lambda, plus, wait a minute. Ooh, okay, I thought I changed this. Give me 1 second. Let me just maybe do this part alone here. So if I write down this, if I kind of rewrite the top equation, what do I get? I get eta times lambda times p of x t minus 1 is upper bounded by p of x t minus 1 minus p x t. And then you get a plus h L squared, eta squared over 2. Right? Something of this form. And then the idea is that I'm going to just sum up these guys and or average up these guys. Right? So if I run this for t steps, I get the following. P of xt minus 1 is less than or equal to, and here it's a telescoping sum. So I get phi of x naught, and I'm going to ignore the minus whatever guy because phi is always greater than or equal to 1. So I get a eta times lambda divided by t plus h L squared eta divided by 2. Okay. So I guess what was wrong on the slide was I had the t here and t not here. It should be this way. Okay. Great. So what does this? Okay. So what does this imply for us? I know that the fees are greater than or equal to 1, right? So I know that this guy has to be greater than or equal to 1. And now what does this mean? Pick some step size. So we pick some step size so that this quantity is less than or equal to half, right? So let's say that I pick eta to be 1 over h times L squared. Okay. Now, if I did this, what this basically implies is that if I run t long enough, then I'm going to get a contradiction because essentially the right-hand side is going to become smaller than 1. Right? So it means that I cannot run for more than those many number of steps before I get a contradiction. So it means that by the time I reach t equal to something like phi of x naught, divided by. So it's going to be eta lambda over p of x naught by 2. I get a contradiction. Okay. So t has to be necessarily smaller than this guy, which is less than or equal to lambda over 2 h L squared p of x naught. Okay. And so this tells you that as soon as you run these many number of steps, then you should at least hit this set of suboptimality less than or equal to epsilon once. Good? No, so here there is, the lambda is on top, right? Here? Here there is no lambda. Oh, sorry, there is a lambda, yes. I have to divide throughout, right? Yeah, sorry. There is a lambda out here. And how does that affect me? So I guess for this guy to hold, I need a lambda up here. So I guess you get a lambda free one then. Yes. So this was the gradient flow one. So this is not for, this is, so yeah, sorry. So this is specifically for gradient flow. That was the condition. I assume that the Lyapunov potential had that as a condition. So Lyapunov potential has the condition that phi is greater than or equal to 1 on and outside of the set of interest. It satisfies the inequality that minus the of p is greater than or equal to lambda times. So these are the two conditions. And yeah, all right. So that gave us kind of one proof that gradient descent converges. The nice part about this, or about writing it this way, is that, so if you've kind of looked at the literature for showing convergence of gradient descent, typically kind of, we have, as I mentioned, like a whole plethora of work that kind of says, oh, if the function is convex, gradient descent converges. And then you have works that show that under conditions like PL and KL, where you have basically some form of gradient dominance condition, gradient descent and gain converges. And then there are a whole bunch of other conditions. There's star convexity, quasi-convexity, quasar-convexity, name it, it's all there. And a whole bunch of these kind of show that gradient descent works. The nice thing about this is you can use this proof to pretty much kind of in a unifying way show that all of these fall under this framework. For each of these conditions, like there is a corresponding phi that gives you each of these. And the nicer thing is that once you start adding noise, you can start kind of using the same analysis for hitting time as well. Okay, so yeah, so the idea is that if you have a Lyapunov function, so if the Lyapunov function exists and it is smooth enough, then you can show that gradient descent works. What I didn't show in this talk is that if you actually had on top of that, that the variance of your gradient is bounded, that is that if you're in the stochastic setting and if you know that the variance of the gradient of small f is bounded by something, then you can also show that the same algorithm works for stochastic optimization, or in other words, as stochastic gradient descent works. Okay. And again, as I mentioned here, I assume that the gradient, that the potential was smooth and that my function was Lipschitz. You can lift both of these to this notion of self-boundedness of gradient norm. And basically what it says is that the norm of the gradient is upper bounded by the function itself. Or some, so the norm of the gradient is upper bounded by some monotonic function of f. Let me write that down. So the self-boundedness condition basically says for a given f, says that gradient f of x is upper bounded by some monotonic function sigma of f of x. Okay. And here again, I'm assuming that f is non-negative. Again, you can do pretty much the exact same thing for as for the gradient with descent with Langevin dynamics. Here, the only thing you need to do is you need to have higher order smoothness and do Taylor expansion to a higher degree. So again, do exactly the same thing, kind of do the Taylor expansion. And then the main thing to notice here, and this I think our friend also pointed out, is we need the expectation. So I'm going to take the expected phi on the left. And so here I'm only taking expectation over the noise I add at the tth round. And then I do the Taylor expansion on the right. And the nice thing is all the linear terms that involve epsilon t are going to disappear because epsilon t's are Gaussian zero mean noise that I'm adding. And then what you will see is that you have this Hessian term here with respect to phi of xt minus 1 with epsilon t kind of, with that matrix kind of giving us the, in a sense, the norm. And that, if you work it out, it exactly evaluates to the Laplacian. Okay, and this is exactly what kind of gives you, so now you have minus of the product of gradient of f and gradient of phi plus 1 over beta times the Laplacian. And that's exactly what was the generator for the corresponding Markov process for the Langevin dynamics, right? And so I can again use the condition that the generator minus generator is greater than or equal to lambda times phi. And lo and behold, I get pretty much the same thing, except that now you also have these higher order terms. And you can do exactly the same argument that we did before, in that if we set eta right, then you cannot run t for too many steps before you actually hit this epsilon suboptimal region. So of course, because it's the noisy version, you might hit it, come back out, hit it, come back out, but it gives you a bound on the first time that you are going to hit it, and that cannot be too bad, okay? So that's the stochastic version. It's pretty much the same proof. It's just that you need to take care of the fact that this noise is added in. And so the second order terms basically give us the Laplacian in there. Okay, so the nice thing is that this definition, it seems like I just wrote this out of thin air. It's not quite that. So two things. One is that for the case of gradient descent, pretty much fundamental calculus will tell us that for gradient flow, you can get gradient flow, gradient flow works in the sense that it gives you a suboptimal epsilon suboptimal solution if and only if such a potential exists, okay? And it turns out that this is also true for the Langevin diffusion. There it requires a little bit more work, and to some extent, essentially the same proof with calculus that you do for gradient flow, you do that with Ito calculus. And so this is there in this paper by Keto et al., where they show that such a potential does exist. And in fact, the potential is exactly e to the exponential of theta times the hitting time for the good set. Okay, and as long as this guy is bounded, you can show that such a potential exists. Of course, the smoothness is a different issue. That requires a lot more work if you can indeed show that the phi is smooth. Okay, but in other words, what this says is that the continuous process works, whether it's gradient flow or gradient Langevin dynamics, it works if and only if the Lyapunov potential exists. Okay, so in some sense, looking for these Lyapunov potential are kind of the right thing to do, at least as far as the continuous time version is concerned. All right, great.
Karthik, in that expectation that you had, is there an initial condition that one needs to keep in mind?
So you mean in the one that I'm pointing to, this one?
I can't see a pointer, but expectation of the exponential function.
Yeah. So the expectation is over your diffusion process. And you want this to hold for every x, at least for now.
I see. For every
starting for every starting point x, you want to say that it eventually converges.
I see. All right.
So about whether you want kind of these convergences starting from, so okay, what is this basically saying? So such a potential exists if and only if this guy is true, right? And what this guy is saying is that not just that the hitting time kind of in expectation, the hitting time is like something good. It's saying that kind of the moment generating function is well behaved such that it has to exist, right? So it has to exist for every single starting point. As long as that happens, it says that such a phi should exist. Okay.
Right.
All right. So great. So that says that kind of whenever if we know that gradient flow or Langevin diffusion works, it has to be true that we can find a Lyapunov function for the epsilon suboptimal set. Okay, good. So Now the next topic, or kind of the next thing that we want to switch to, is sampling. And specifically, one of the things that's, or one of the main techniques that's used in sampling, or main assumptions that's used in sampling, is some form of isoperimetric inequality. I'm going to do the simplest version. So we are going to assume, or we are going to kind of think about measures that satisfy Poincare inequality. Okay, so specifically, a measure mu on R to the D is said to satisfy Poincare inequality if the following happens. There is some constant, we'll call it C sub pi, such that for every single infinitely differentiable function f, the variance of f can be upper bounded by the constant times the expected value of the norm of gradient square. Okay, so this is the Poincare inequality, and it turns out that if you replace variance here by entropy of f squared, that's called log Sobolev inequality. It's a stronger version, and what we are going to be interested in is basically taking this mu to be mu sub beta, where mu sub beta has exactly the density given by the Gibbs distribution. So you have our capital F, and the Gibbs distribution with respect to capital F at temperature beta, that's going to be mu sub beta. Okay, and we are interested in when, we're going to look at the cases where our mu sub beta has these Poincare kind of inequalities hold for them, and how this is connected to optimization. So one thing I want to mention is that a function capital F satisfying, I'm going to say that a function capital F satisfies Poincare inequality if its corresponding Gibbs distribution at the temperature beta satisfies this pi inequality. And one thing to mention is that oftentimes look for a capital F to satisfy pi is much weaker than conditions like convexity, PL, and KL. And one version of seeing this is that whenever F is convex, then the corresponding distribution is always log concave, and it does satisfy pi. This is more classical results. But the interesting part is that you can also get this for functions that satisfy KL and PL. A little bit more about it as we go. Sorry, so these are the gradient dominance conditions. So as I told you, there are conditions under which you can show that gradient descent works. PL is something of the form, let's see. So gradient F squared is upper bounded by, let's say, lambda times F. Something like this. Okay. So gradient dominance condition. This is PL. KL is like a more fancy version where you have like a polynomial on the right. Sorry? Inequality is the other way. Sorry, yes. Thank you. Yes. Yeah. So in fact, if you want to show that gradient flow works from everywhere, it already implies that all local minima have to be global minima, right? So the fact that I'm starting, like my starting assumption that gradient flow works from everywhere kind of already implies this. PL is a very specific way in which this happens. KL is kind of a generalization of this. And there are more generalizations. So the way I kind of think about it was through the generator. So you can think of it as gradient phi of x times gradient f of x is greater than or equal. So one version of this, it's not exactly what I showed in the slide, is that this is lower bounded by some monotonic function g of f of x. Okay, so my claim is that depending on what phi you use here, different phis here will give you different kinds of quantities. Like, so if you, for instance, you take phi to be, sorry, I forgot the gradient here. This is gradient. So if you take phi to be f itself, then you get exactly the PL condition. If you take phi to be x minus x star, where x star is the minima, then you get convexity, or kind of what convexity implies. You get kind of the linearization, and pretty much all the conditions for which show that gradient descent works from anywhere will, for all of them, there is some corresponding phi that will kind of give you those conditions. And I guess for KL, you do the same thing, except that there is the G function here. You have to, it's not just identity, it is some other function there. No, this is an assumption. I'm saying that there exists some phi and some monotonic G such that this happens. And again, I'm assuming that minimizer of f is 0. And then, yeah. Great. Okay, so back to Poincare. So there are much weaker conditions. Okay, Poincare is kind of weaker than KL and PL and so on. And the nice thing is that if you have Poincare condition, if your measure satisfies Poincare inequality, then what we do know is that Langevin dynamics works, meaning that if I run Langevin dynamics from any initial distribution pi naught and go up to time pi sub t, then I know that the chi-squared distribution kind of chi-squared deviance with divergence with respect to our original measure kind of decays exponentially fast. Okay, and okay, and from existing literature, kind of with enough properties on the sorry. Yeah, so with existing literature, with enough regularity assumptions on f and so on, you can also make, you can also come up with discrete time algorithms that get us this. And all right, so great. So what we have from that is that Lyapunov functions exist if and only if we can show Poincare inequality holds. And if that happens, you have sampling as well. Good. Now, I'm going to skip this. These are kind of results that you can improve based off of kind of constructing potential this way. Good. So where does all of that leave us? So essentially, it tells us that on the deterministic side, gradient flow works if and only if such a Lyapunov function exists. And if that happens, it implies that gradient descent works. If you have additional smoothness on phi, and if you have additional conditions on variance of the gradients, then you also know that stochastic gradient descent works. And similarly, on the stochastic side, you have that Poincare if and only if such a Lyapunov potential holds. And if that happens, Langevin dynamics works. All of these are equivalent. And again, with higher order smoothness, you can get that gradient Langevin dynamics works. And with variance on gradients being bounded, you also know that SGLD for a learning algorithm works. Now, the other interesting part is that there is a connection that you can make between existence of kind of the Lyapunov potential, or basically the fact that gradient flow works. You can show that that implies that Poincare inequality holds for appropriate temperature. So specifically for temperatures beta that are big omega of d, that are d are larger, and as long as you have that for the measure near the optimum, you have that some kind of local Poincare inequality holds, you can show that the Poincare inequality kind of extends to the entire space when you consider kind of the Gibbs distribution with respect to this corresponding beta. Okay, so let me.
The question here. Yeah. How much of this continues to hold if you add momentum, for instance, to gradient descent or use something like ADAM?
So we haven't tried that. So I guess, so typically when you add momentum, it's, so I guess once you add like momentum, for instance, you need to, I guess like, so the way we work out the potential is all in the continuous time, right? And so we need to figure out what's like a good way of kind of representing the continuous time version. Trying to think of whether we did this. Right. But so you're claiming that that's the, so I guess the way I'm discretizing here is based off of the existence of the potential, right? So, right. Right, but I guess like I don't see the connection, or I don't yet see the connection of kind of, so it could be that is like if you kind of think about adding momentum, you could directly use that potential. I see. So I guess I know about Hamiltonian MCMC. I guess like I don't know whether this mechanism goes through between like, for instance, if you know that the optimization with momentum works, does that have like, I mean, that has correspondence.
I see. So just the claim is that the momentum, the continuous version you would write as a second order differential equation, and then you convert it to two first order differential equations and use the same techniques. Is that the intuition of what you're saying?
I see. All right. I guess I'm assuming that works. I haven't tried it out. Yeah. All right. So what we can also show is that if you have the Lyapunov potential for gradient flow, then it also implies that Poincare inequality holds. And of course, when you want to do this, you need some conditions. So first is that the temperature has to be omega of D or larger. And luckily for us, a lot of kind of the ML applications, while you don't want beta to be, while you don't want the temperature parameter to be like a large polynomial in D, linear in D is fine. It's okay for many applications. And so that's a good thing. And the second thing is you do need some kind of a local PI around the optimum. And that's fairly easy to see. So imagine I had a function where capital F, where the set of minimas look like this. Okay, so it looked like a large dumbbell with a very small gap in between here. Okay, and I can set up this. So this is the set of minima, and then I can set up the function to kind of be nice going outwards. And now if I basically run gradient descent, it's going to easily kind of settle on any one of these, right? So the fact that gradient flow works is going to be fairly easy for this because all of these are the set X star is basically all of this set, and they're all the minima. And gradient flow works because anywhere outside I start, I can kind of make it kind of travel easily towards the set here. On the other hand, sampling from such a set using Longin Monte Carlo is going to be super hard because if I start from some arbitrary distribution, like let's say a Gaussian out here, it'll sample well on this part of the ball, but it's not going to go through this region here, right? So mixing time is going to be horrible. So this basically tells us that you do need some extra condition for Poincare inequality to hold, specifically that, okay, gradient flow will kind of get us towards this minima, but then you want kind of the set of minima to have nice enough properties, right? And so specifically, sorry. That's the condition that we are going to write down. So the condition we want is that a local Poincare assumption holds. So specifically what we need is that for a small enough L, so think about L as like the suboptimality, what should happen is that there exists some radius R such that the set of L suboptimal region is a subset of the ball around R X star. So X star here is the set of minima, and ball around X star is basically just take all points that are R of L close to X star. Okay, and you want Poincare inequality to be satisfied here, and let's say CPI local is the Poincare inequality within that set, or kind of when I restrict the measure to that set. Okay, and there's another condition that I'm going to write down here. In the literature, it's a slightly stronger version of it is called dissipativity, but for all practical purposes, they are kind of similar. So I'm going to call it dissipativity as well. It basically says that there is a large enough radius such that once I kind of go far out from this function, then it kind of has a property that looks like convexity in that the gradient is pointing towards the minima. So specifically, it says that there exists some X star in the set of minima such that gradient F times X minus X star is larger than F of X. Okay, so in other words, it kind of points towards the set of minima. And it should also be that as I go farther and farther out, F of X can just be lower bounded by kind of the distance to this point X star. Okay, these are fairly natural conditions that one assumes typically seen in sampling literature. Okay, so the result that you can prove is the following. When your temperature is larger than D, under the assumption that mu beta is locally satisfies the local Poincare inequality, and you have dissipativity, we can show that as long as F is optimizable using gradient flow, or in other words, it satisfies the Lyapunov condition, what you can show is that the measure mu sub beta satisfies a Poincare inequality with a constant that looks like the local pi plus 1 over beta. Okay, and I'm hiding here constants that come from the two assumptions in my previous slide. And you can also, once you have kind of under a weak convexity and quadratic growth as you go farther out for F, you can also show that this can be strengthened to log sublevin inequality. All right. So before I go into kind of a very rough proof sketch, let's look at implication of what this means. So first is it says that you can obtain kind of poly d comma 1 over beta type for poly d comma 1 over beta type results for non-log concave measures. Specifically, it means that you can get kind of isoperimetric inequalities that are poly in d comma 1 over beta for f's, for instance, that satisfy PL condition and KL condition and so on, or for quasi-convex x's, f's and so on. And so I think kind of even like if you look at literature for when Poincare inequality is shown for PL, that's also, to my knowledge, mostly like fairly recent. And the nice thing is it kind of comes out pretty much from this Lyapunov potential. And again, it tells us that you get nice sampling rates, specifically that are poly d 1 over beta and 1 over epsilon for such functions. Okay. And again, here beta has to be of order omega of d. And so to give some perspective here, under fairly general conditions on F, you can show that F satisfies Poincare inequality, but typically the Poincare constants for these results are exponential in D. So to get something that's poly D requires more work. And this one, it basically says that optimizability somehow gives you the criterion that's required for getting these nicer rates for, or nicer constants for Poincare inequality, and hence also for sampling. It means that the Lyapunov potential for gradient flow exists the way that I mentioned. Right? So because if gradient flow works, then the Lyapunov potential with those properties exists, and so they are basically equivalent.
You said that it's a fairly good assumption that the function is locally PI. So why is it a good assumption?
Oh, I didn't. So okay. So I said it was a fairly okay assumption for the dissipativity. For the PI, I'm not saying that it's a good assumption. I'm just saying that for the locally PI.
Yeah.
So I'm saying that you cannot expect the measure to be PI if you don't have local PI. So all that I'm saying is that, okay, so gradient flow kind of tells you something about the function, about how the function kind of, the fact that gradient flow works says something about the function outside. But once you go into the set of minima, this set should still be mixable in some sense, right? If you start like a Langevin diffusion, under that set, everything is flat. So you should be able to traverse everywhere in that set. So if that set looks really bad, like if it looks like this, then you're kind of host. Right? And in general, like if I just told you this is your set, sample from this uniformly, it's going to be hard in general, right? Because you have to kind of pass through this region. And that's about it. Okay. Again, all of this is like assuming you want kind of results where you start with any distribution, right? But for instance, this is easy to sample from. For instance, if I gave you kind of one blob here, one blob here, and then I said start from that. So Poincare inequality or any of these isoperimetric inequalities basically imply that you get convergence starting from any initial distribution. And that's not the only way we can sample from. You could, for instance, have a warm start. And that's a different thing. So here, all that I was trying to say here is that this local PI is necessary if you want to get PI for the entire measure.
Okay.
It's not that you want to sample, you want to sample, let's say I give you this set and I say sample uniformly from this set. Yeah. So let's say that I just tell you sample uniformly from this set. Right? Now, if I ran a Langevin diffusion process, starting or Langevin dynamics starting from like, let's say like a blob out here, like uniform distribution or a blob out here or something like that. Or even I could basically make it a Gaussian. So let's not have like the measure being 0 outside. So let's just say it's a Gaussian but centered out here. Then it's going to be very unlikely that you'll traverse here, right? So you're not going to converge to the uniform distribution over the set. Right? So there is some condition that you need that is kind of outside of whether gradient flow works or not. Gradient flow works or not tells you things about what happens outside of the function, but with, outside of the set of minima. At the set of minima, you need some kind of regularity, and that regularity that I'm assuming is basically what I showed there. The fact that locally, like if I expand the set a little bit, the corresponding set, and then if I restrict my mu to that set, it should satisfy pi. And if it satisfies pi, then we are good. And that's kind of that's necessary, yeah. So here here when I write down that gradient flow works, I'm basically saying that you have a bound on when the hitting time, you have a bound on the hitting time, right? And then the bound on the hitting time is kind of like, for each point, the bound on the hitting time will imply the phi of x corresponding to it, right? And I guess that is pretty much the condition, right? Like if you don't have a hitting time, if it is not bounded, then you're toast, because it says that starting from that initialization, you're never going to converge. Right. So for gradient descent, I don't know. For gradient flow, this will tell you that. If this condition is satisfied, then it'll yeah. So all of this is great except for you don't know regularities on phi. So the momentum, I have not worked it out, so I don't know what happens with momentum, because it's not like so this one is ODE, and then the other one, it's a first order, right? The other one I haven't tried it out. So I guess both for the momentum, the deterministic momentum version, and for the diffusion momentum version, I don't know what happens.
There's some connection between this kind of picture and the eigenfunctions of the generator in the reversible case, where the eigenvalues and eigenfunctions are real.
I see.
So, suppose if there's zero eigenvalue corresponding to you go to the next eigenfunction. It will have different signs. The signature.
Right.
It will be positive on one side, negative on the other.
So I guess the fact that this one mixes well is connected to like Cheever constant and so on, right? So that's probably what is getting. Right. So you can convert this result, basically the local PI, like the upper bounds on local PI, you can get exactly using spectral gap. In some sense, once you go within that set, it's exactly the spectral gap result. And then outside of the set, we are just using properties of gradient flow. So that's exactly the way to think about it. And so yeah, I think kind of, so if you look at the thing here, so essentially what this is saying is that this set, we say whatever you pay there, right? And then typically, like if you look at the spectral gap results, they are exponential in spectral gap and so on. That will come here, and that's unavoidable. But that's only when you look at the set of minima, or like kind of the expansion of the set of minima. But if for instance, let's say you're thinking about like, a function that's, let's say, convex, or has like properties where this set is even, for instance, let's just say that you had a unimodal function. And if I had a unimodal function, all of this disappears. This guy is just zero, right? Because there is just one mode, and then like you expand a little bit out, there's a little bit more that comes because of the expansion. But as long as kind of near the mode things are nice, this part completely goes away, right? And then what you are paying is polynomial in 1 over beta. Now, if this guy has like a exponential dependence in spectral gap or in dimension, that's unavoidable. But that's unavoidable for good reason, because it's really there and there. But what I'm saying is outside of that, you don't need these kind of heavy dependencies. All right, so some implications before I go into a rough proof sketch. So, okay, so the idea is that using this, you can get isoperimetric inequality, specifically Poincare inequality, for a whole bunch of non-log concave measures. So specifically ones where F satisfies like the typical conditions that are used in optimization. And so to some extent, it kind of directly opens up a lot more functions where we can kind of use these type of sampling methods. And I guess, as I already mentioned, whenever you have things like Poincare inequality or log-Sobolev inequality, it means that you can start from any initial distribution and you can kind of reach, or you can kind of sample from the right or close to the right distribution under whichever distance exponentially fast. And with some additional smoothness properties, you can actually kind of convert these to discrete time. You can get poly d 1 over beta 1 over epsilon type results when you're looking for, where here epsilon is the TV distance between my the distribution that I give and the target distribution. Okay, so now let me just give a very short. I won't be able to kind of give a detailed proof, but I'll give a proof sketch that hopefully shows you the idea. Okay, so I'm going to define the set U to be the ball around the minima of length R of L, right? We know that such an L exists from our assumption. And let's say that psi is any test function. Okay. Now what I'm going to do is first I'm going to define my function f as psi minus alpha, where alpha is the expected value restricted to this set. Of psi. Okay. And now we're going to start with the following. If you look at variance of psi, that I claim can be upper bounded by okay. So the first claim that I'm making is that variance of psi can be upper bounded by f squared. That's fairly clear, right? And now what we're going to do is we're going to split this up into two sets. One is within the set U, and then outside of the set U. Okay. And now you should already be able to see why I defined f the way it was, because f is defined as psi, right, minus the expectation of psi within the measure, but only within the set U, right? That's how I've redefined it. So in other words, this guy is exactly the variance of f, of psi, right? And so I know that I can upper bound this guy by using local PI. Right? So if I did that, I'm going to get that this is less than or equal to, so here I'm going to use the local Poincare inequality. This tells me that this is CPI local of, what is it, integral over U gradient of, psi squared, right, d mu beta. And then there's a mu beta of something of this sort. Okay, good. And then what am I left with? I'm left with this guy. This is what we need to kind of handle more carefully. So here we're going to do the following. Okay, so here I'm going to use the fact that, so first I'm going to kind of multiply and divide by phi. Okay. And I'm going to use the fact that I can, that phi has an upper bound, right, which is whatever is there from the generator, right? So using the fact that lambda times phi is lower bounded, sorry, is a lower bound on minus the Laplace operator of phi. So I can use that guy here. So that gives me that this is less than or equal to CPI local d mu beta plus, now for this guy, I'm going to use the minus Laplacian operator of phi with an f outside. f squared outside divided by phi d mu beta. Okay, good. And now the idea is the following. I'm going to take this one out. Okay, and then now again, if you attended Dheeraj's talk, one of the main results or kind of one of the tools that was used the most there was integration by parts. So you can do integration by parts on this guy, and that gives you that's going to give you something nice. So that's on the left hand side I had f squared d mu beta, right? And then on the right hand side on one of them I had what I wanted, which is oh, sorry. I'll just erase this. Okay. So left hand side f squared d mu beta, right hand side is beta u d mu beta psi gradient psi squared. Did I write gradient psi squared or something else there? Okay, good. Plus, wait, who did I? Okay, good. So now I'm going to use integration by parts. That gives me essentially the following. It's going to give me, I'm going to get gradient of f squared divided by phi transpose gradient phi. Okay, d mu beta. Good. And I guess one thing is here when I went from U to putting it on the entire set. Sorry, where did I go? Here. So I went from U complement, I put it to the entire set because this is non-negative. So I'm allowed to do that. So this is on the entire set. Okay, good. So we have this. Now we just have to do calculus, right? So this part from there to here was from integration by parts. And now let's write this out. The first term, I'm just going to write it as first term plus, what is this guy going to look like? This is going to look like two things here. So 2f divided by phi gradient f times gradient phi. And then I'm going to have a minus of f squared divided by phi squared, and then gradient phi squared. Okay. And then let's put a d mu beta here, d mu beta here. Okay. All right. Now what else do I need to do? Okay. Now I need to. It's something. Am I missing something? Oh, sorry. I used the Laplacian from the wrong equation. Let me just. Sorry. This one is so this was the general condition, right? This one was for the Langevin dynamics, right? But for the Langevin dynamics, the Laplace operator was minus script L for gradient flow of phi, and then it had an additional term which I'm going to write it as plus Laplace operator on phi with a half here, maybe with a 1 over beta. Sorry, 1 over beta here. Okay, because remember that I don't want to show that gradient flow. I don't want to show that sampling works when this condition holds. I want to show that sampling works when gradient flow has the condition. So which means that I'm going to take the the generator for gradient flow, and that has an additional Laplace operator over phi. So. Yes, thank you. I'm missing my lambda. So for all practical purposes, for now, just think of lambda as 1. It's just going to be annoyingly there everywhere in the denominator. So let's just make this condition for now as just this guy. Okay. So the idea is that what we know is, so sorry, I should have, that was not ideal. So the condition that we know is the following. Okay. Okay, let me just write it out here. So I haven't yet used the operator, so let's do it out here. So I came all the way to here, good. Now the idea is that what do we know this is upper bounded by? We know that this is upper bounded by, oh no. Great, okay, sorry, I messed up here. So this is, so there is a minus L here, and then there's going to be a plus integral d mu beta p divided by 1 over beta, okay? And where is this coming from? Because the condition that I have is that phi is upper bounded by this guy for gradient, sorry, this guy for gradient flow, right? So what I had was, so I know that phi is upper bounded by, again, I'm missing out the lambda, so it's phi is upper bounded by gradient phi times gradient f, right? And this guy is upper bounded, sorry, this guy is equal to Laplace operator under Langevin dynamics of phi. But then I have to also remove the other Laplace term, so that gives me of phi divided by beta. Okay, and that's where this guy comes from. Sorry about that. So there is the gradient flows generator, and then there is the Langevin dynamics generator. I need to go to the Langevin dynamics generator. So I first start with this guy. I know that this guy is, so I know that phi is upper bounded by gradient phi times gradient f. And then what do I need to add to make it into the Langevin dynamics generator? It's going to be plus this guy, right? Plus Laplacian of phi divided by beta. Because that was the generator for Langevin dynamics. And now I plug that back in here. So I have one extra term here, which is plus integral d mu beta. And then I have a phi divide 1 over beta, this guy divided by, actually there's no divided by, I think. There's f squared, sorry. Okay. All right, so now the main thing to notice here is that I can use, okay, so now what I can do is I can do Cauchy-Schwarz here. And then what do I get out of it? I get that this whole thing is upper bounded by 1 plus integral gradient f squared under d mu beta. That's good. And then I'm going to have like a plus another term, which is integral f squared divided by p squared, gradient phi squared. Okay, and I need to balance the constants appropriately. So I'm going to leave this with a 1, and then I pay like a 4 or 16 or something here. What this constant is, I don't remember. You just have to manipulate the constant so that you get a large enough constant here. And then what you get is this guy here, right? But this is good because this guy, this was just this term here, right? And this guy exactly cancels with this one here. And so the only thing now you're left with is this last term here, okay? And now the last term, as long as, so the one thing that I did not show you guys is, first I didn't show you where the, I already showed you where the local PI is used. What I didn't show you guys is where the dissipativity is used. So the nice thing about the dissipativity is it says that within a small, I mean, within a reasonable ball, things are good in that you can kind of, you have a phi. And then as you go farther away, you can basically replace the phi by just norm squared. Because it basically says as I go farther and farther out, basically my set kind or my function looks like it's convex, right? So the idea is instead of using the phi that you originally were given, you modify it outside, kind of outside of this large radius, you modify it to be like quadratic. And inside you can kind of modify it to be pretty much what it is. And in the end, what it means is that you can get phi to be smooth. Phi can be made H smooth. Okay? So phi can be made H smooth. What does that mean? It means that the Laplacian operator on it is upper bounded by d times h because it's d-dimensional. So this whole thing, I can upper bound it by 1 plus 16 times integral gradient f squared d mu beta plus something that looks like d h times d divided by beta and then integral f squared d mu beta. Okay? And now what's on the left-hand side? Integral of f squared d mu beta, and on the right-hand side, hd divided by beta d mu beta. So as long as beta is larger than, let's say, h times d times 2, then this becomes half of the left-hand side, right? And then you're pretty much done because in the end, all of this implies that integral f squared d mu beta is upper bounded by 1 plus 16 times integral gradient f squared d mu beta. Okay, and again, notice what 1 is. 1 is already kind of what we wanted. It has the gradient of psi, which is our test function. Now, the final thing to notice is that variance of f is always upper bounded by variance of psi is always upper bounded by integral of f squared d mu beta. Why is that? Because this guy is equal to integral of psi minus alpha squared d mu beta. And alpha is not necessarily the minimizer of this side, right? So if I essentially pick the minimizer, which is exactly the expected psi, that gives me variance. So I have this bound here, okay? And so in the end, what does this mean? This says that this is lower bounded by variance of psi. So it says that for any psi, I have kind of the right inequality because 1 also has pretty much this term in there. Okay, so the actual proof requires kind of more work because I told you you can do the smoothing. It requires quite a bit of work to kind of get the smoothing done and kind of constants pop up as you go along. But kind of this is the high level kind of sketch of the proof is this. And what this says is that as long as you have your as long as you have kind of the gradient flow works condition, which is this guy, then from that you can imply that Poincare inequality holds. Can I just get very quickly one switch again to the slide? I just wanted to conclude once. Okay, so just to very quickly conclude, so one of the things that kind of one might ask is, it's typically not true that gradient flow kind of works from anywhere in your space. Typically, the results that you have is that you have a good initialization set. You start from this initialization set and then gradient flow works and gets you to the minima. And the idea is that in this case, you can get something weaker called weak Poincare inequality. And weak Poincare inequality says that it's kind of like Poincare inequality, except that you pay like a delta factor, delta times oscillation of f. That is how much f can switch between its max and min, okay, squared of that. And the idea is that if you have weak Poincare inequality, then you can kind of still, so if you have weak Poincare inequality, while you cannot start from any arbitrary distribution and converge on sample, what you can show is if you have kind of good warm start distributions, then you can converge. And the nice thing is that kind of pretty much the same style of mechanism with a little bit more work actually gives you the result. So specifically what you can show is that as long as the temperature is larger than d order d, then mu beta is locally satisfies local Poincare inequality. If we have that f is optimizable using gradient flow, but only on some nice initialization set S. What I mean by that is that this inequality holds only on capital S. Then what you can show is a weak Poincare inequality where delta is basically the measure outside of the set. So of course the one issue is that if your measure mu b puts a lot of weight outside of good initialization sets, then you're going to be in a bad position. But in that case, you should also not really expect kind of optimization-based methods to work well, because it means that you're covering a lot of grounds and kind of bad initialization regions. Okay, so using this, you can also kind of have versions where you might have like kind of measure zero sets of kind of bad initial points, and that's all fine as long as you have a good warm start. right? So that's about it. I think kind of the rest, kind of the high level picture is that there's this kind of strong connection between optimization and optimizability and isoperimetric inequalities, and kind of it kind of goes through this Lyapunov potential idea. Kind of a lot of the Lyapunov potential version that I use here is by Keto and I forget the last name, Guillaume, maybe. And kind of, and that's where kind of we took the Lyapunov potential definition, and it basically says that kind of there's a strong connection, which means that in a layman's term, basically it says that you have isoperimetric inequality whenever you can optimize using gradient descent, and this means that optimizability implies that at least at temperature regimes that are D or larger, you can sample from the Gibbs distribution, and vice versa also holds, as I mentioned earlier. Okay, and kind of the nice thing is using this, now we know that sampling holds for a bunch of functions that go beyond kind of log concave distribution. Because if you look at the sampling literature, mostly what's covered there are log concave distribution, and only recently people have been kind of trying to move towards non-log concave distributions. That's about it. Thanks.
I have a question. So for optimization using gradient descent, we said that if gradient flow converges, then yeah, and maybe if you add a little bit more, like local PI, then you can get sampling from the appropriate distribution. So do you think that maybe some result like this also for the case when maybe some perturbed version of gradient flow converges?
So, okay, so that it becomes, so if a perturbed version of gradient flow converges, right? So first you need to kind of fix what you mean by converge there. So when you say perturbed version of gradient flow converges, there are two things you need to say. What is the rate of perturbation, right? Because you're going to, like, let's say you're talking about like Langevin kind of method,
exactly.
right? You're going to add beta times some noise or whatever. Now that beta is going to be important, right? Because it's going to tell you kind of, because there is the notion of what's the perturbation that you add, and then what's the Gibbs temperature at which you want to sample.
Right.
So if you basically say, I want to kind of, the beta that I multiply to the perturbation is the same that one where I want to kind of sample from, then you need to kind of say, okay, you're claiming that this one converges. There are a few more conditions that are required, at least for getting, so if you want, so the only kind of caveat of using this method is that the way kind of, at least like the potential I wrote down works, and I think this was mentioned by him as well, is that the way it's written down, it's kind of it's a condition that says that the moment generating function of the hitting time is like well behaved.
Yes.
Right? You might have versions where you're just saying that with some constant probability, the hitting time is going to be as small as this. Right? So that's kind of a fairly weak condition. And if you have that, then that still counts as like gradient descent with noise working. Now it's not clear kind of what that implies, right? Now, of course, you could basically say, I can kind of try to relax these conditions, like from going from phi upper bounded by whatever, you can try to relax them. So again, I don't know the literature very well, kind of. So I think he probably might be able to like give us better idea, but there are kind of these, so there's Poincaré on one side, there is log Sobolev on the other side. From what I know, or kind of from the Ghetto et al., like what I showed you is what Poincaré, like guarantees that Poincaré holds. Log Sobolev holding requires, I think, slightly more stronger conditions. And then there are things in between that are called like F Sobolev or whatever. But presumably you could go weaker than that as well, right? But now the question is, okay, if you go weaker than that, then you would get some potential out of it. But then now it's not very clear whether from that, so okay, you could go weaker than that, you get some potential. Clearly from Ghetto's result, it's okay, I'm bad with names, sorry. So clearly from the result that I mentioned, Ghetto's result, like it is, you're not going to get Poincaré inequality. You might get something weaker, but it's not also clear to me kind of from that how far you can go in terms of showing sampling works. So the weak Poincare we showed, because weak Poincare, there are results, recent results that kind of show that with the right warm start and right annealing technique, you can get results. I mean, you can get sampling, but it also says that right warm start. Of course, there are many ways of weakening Poincare, right? Like if you weaken it in other ways, I'm not sure what happens. So I think kind of the short answer is, for the noisy version, if you tell me exactly what you mean by it works, in that like when do you mean like with constant probability it works, or whether you have like some kind of a concentration on the hitting time. So this one, the way I am kind of writing it down, it kind of says that it's all its tails are well behaved, right? So it's saying that the hitting time, it's not just that I have like a constant probability bound, I have like I have the nice property that expected exponential of theta times hitting time is bounded. Right, so that's like a stronger result in some sense.
Yeah, because I think that in these such a concentration kind of a thing would hold for some kind of perturbed GD for these functions which are which have some property like strict saddle point and Hessian smoothness, and Praneeth would know better. So this is true, right? So if a function has Hessian smoothness and strict saddle point, then perturbed GD will actually give you concentration of the hitting time. I mean, it's not just hyper, or maybe I'm wrong.
I mean, it's still the optimization setting, right? Because you're talking about hitting time to an epsilon suboptimal region. So it's like the first time you hit the region. So again, kind of, so I think kind of a lot of the results out there are actually like fairly strong in that it's not just hitting time. They can even show you that that kind of after you kind of hit the, like the number of times you leave that region is very small even. So there is a whole bunch of results for which you can extract out the hitting time, kind of like a bound on the hitting time. But again, like my point is, if you want to make a general statement that says that the perturbed version works, does that mean that you have like, let's say, isoperimetry? That I don't know, because you need to kind of specify what works means. So here, when I say works, I mean very specifically that the for the perturbed version, I mean very specifically that the moment like the expected exponential hitting time with some theta is bounded by bounded, right? But yeah, but the nice thing is for gradient flow, all of this goes away because it's all deterministic. So if it works, then any of these, and then you can kind of put that condition down there.
Great. Okay, thanks. Yeah, but right. Yeah, exactly. So I'm wondering if in that setting, it's much faster. Then can you extend that?
I mean, presumably you could also try to do all of this in higher order, right? Like, so for instance, you could take something like take kind of one of the higher order methods, like cubic regularization, whatever, and then try to, so people have worked out kind of the continuous time version. And then you could try to do all of this, kind of ask what's the right generator there, and then kind of do this mechanism. Again, my gut feeling is that it should work. I haven't tried it out, but that goes to a different ballgame, I guess, because then you start getting different types of convergence. Because right now, kind of in some sense, the convergence that you would expect, like the constants and stuff that you would expect, will be like what you can get best with first order method, right? When you go to higher order methods, you get like different types of dependence. Like you can relax kind of the type of like whether you need like bound on like the higher order gradient everywhere, or whether average and all of those things will start popping in. This was our first attempt, so I don't know whether like my gut feeling is that it should go through, but then also there is like a lot more calculus that will be involved. So I mean, I'm guessing it should probably go.
We can talk offline. Any further questions? Any questions online? Okay, thanks. Okay. Let's thank the speaker.